We next want to look at the electric potential and potential differences on and in conductors. So one of the things we know about a conductor is that if it's in electrostatic equilibrium, all of the electric field points perpendicular to the surface of the conductor and all of the charge lives on the surface. So we can imagine taking one of these charges and moving it from point A to point B. So if we do that, we know its change in potential energy is going to be equal to Q delta V. We know this because the potential difference is defined as being the difference in potential energy divided by the charge that's moving around. And so the change in potential energy, just rearranging that expression, is equal to the charge times the potential difference. So the work we know is the negative of the change in potential energy, and so that's going to be equal to the negative of the final potential minus the initial potential times Q. We also know that the work done moving a charge from one point to another, from point A to point B, is equal to the charge times the component of the electric field in the same direction as the displacement times the displacement. Now in this case, since we're moving the charge along the surface of our conductor, the electric field is perpendicular to that surface. There's no component of the electric field in the direction of motion, so that this electric field component in the direction of motion is 0, so the work done in moving the charge from point A to point B is also equal to 0. But if the work is equal to 0, then there must be no potential difference between point A and point B. So in moving a charge from point A to point B on the surface of a conductor, the potential difference is 0. That means that the electric potential is constant on the surface of a conductor. The voltage is constant. So if you were to find the voltage at any point on the conductor, the voltage is the same everywhere else on the conductor. Also, we can think about moving the charge inside the conductor. If our point B was inside the conductor, well, we know that inside a conductor with electrostatic equilibrium, there is no electric field inside a conductor. So once again, the electric field here is 0 and there is no potential difference. So that means that the potential difference is the same inside a conductor at all points as on the surface of a conductor. So that's a really convenient principle because it means that if we want to find the potential difference and we have our multimeter and we're using it to measure voltage, it doesn't matter where on a conductor we put our voltage probe, we're going to get the same answer because all of the points on the conductor and inside the conductor too are at the same electric potential. They're at the same voltage. Now it turns out that there is a very convenient energy unit that we use when we talk about charges being accelerated by electric fields. And this new energy unit is called the electron volt. And it's defined as being the kinetic energy that's gained if an electron is accelerated through a potential difference of 1 volt. So we know that kinetic energy is equal to minus the charge times the potential difference. That's how much work is done moving a charge through some potential difference. And if the potential difference is 1 volt and the charge is the charge of the electron, we get a change in the kinetic energy of 1.6 times 10 to the minus 19 joules. And that is defined as 1 electron volt. So if you allow a potential difference of a volt to accelerate an electron, the electron will gain 1 electron volt of energy. If you have a 5 volt potential difference, the electron will gain 5 electron volts. If you have a 10 volt potential difference, the electron will gain 10 electron volts of kinetic energy. The kinetic energy that's gained is the same as the potential difference in electron volts. And then you just need to do a unit conversion to convert from electron volts into joules. And it makes some problems a lot easier to have that tool. So next I want to talk about another way of graphically depicting what's going on around charges and looking at the electric fields, but also looking at the what's called equipotential surfaces, which gives you an idea of what the electric potential is around these charges. So equipotential surfaces are lines or surfaces on which the electric potential is constant. So we know that for a single charge, as you move away from the charge, the electric potential, which is Keq over R, goes down. And these blue lines, these blue dashed lines, show us where lines of constant electric potential or constant voltage lie. So if you were to go anywhere on one of these circles, you would find that the potential is the same. And similarly for over here, these blue dashed lines are lines of constant voltage, constant electric potential. No work is required to move charges at constant speed along these surfaces. And you'll notice too that these surfaces, these lines of constant electric potential, are perpendicular to the electric field lines. So if you want to figure out where they should go, then you know that anytime you cross an electric field line, it is perpendicular. And the same over here. Every time you cross an electric field line, the line of constant voltage or constant electric potential is perpendicular. So if we think of electric potential as being the height for positive charges, the equipotential surfaces are like the lines on a contour map. So the way a contour map works is that it shows you the elevation profile by having lines that are drawn at constant height. So let's say we have an island here, and we can see where these lines of constant height are located. And so if you draw a bird's eye view then of this island using this contour map technique, these lines will then show you where the height is constant, and then you can see where the height increases to the next marker. And by looking at how close together these lines are, you know how fast the height is changing. If you were to walk in this direction, the height would be changing faster than if you walked in this direction because you cross these contour lines more quickly. And in this picture is an actual picture of a contour map, and this we can see is a mesa. It has a flat top, and then the lines of contour or positive or constant height, the lines of constant height wrap around this mesa, and so we can tell that if we were to walk in any direction, we would be going fairly steeply downhill. And over here, it looks like the lines are slightly closer together, so you have a bit more steep of a descent. So next, let's look at this question. An electron initially at rest accelerates through a potential difference of 1 volt, gaining a kinetic energy Kee, while a proton also initially at rest accelerates through a potential difference of -1 volt, gaining kinetic energy Kep. Which of the following is true?